You're welcome to day 12 of the 50 days of tutelage. I'm going to be continuing with the chemistry class on chemical bonding. I've already taught a lot in part 1 of this particular class. I had already explained about ionic bond majorly, where I explained that electrons are completely transferred from one atom to another atom. And I told you that these atoms that actually transfer the electrons, they are perfect donor, and the electrons that receive this electron, they are perfect receiver. So the if you want to understand more about the whole thing, you can just go back to the previous chemistry class and then you'll see everything there. So today we're going to be talking about chemical bonding, and then the major things I'm going to be discussing in today's class, of course, the second major type of bonding, the covalent bond. I'm going to be discussing about the covalent bond. I'm also going to be discussing about Lewis the Lewis dot structure. I'm going to be discussing about the Lewis dot structure. Then I'm going to be talking about the VSEPR theorem, that is talking about the shape of molecules. Then I'm going to be talking about the polar covalent bond as well. Polar covalent bond. So these are going to be my major focus for this video. So if these things sound like what you would like to know, then stick around long enough in this video. So let's get into it. What is covalent bond? It happens that there are some times that some atoms will not be able to lose electron or will not be able to receive electron due to one reason or the other. But they still want to complete their outermost shell with 8 electrons. They want to attain the octet or the duplet structure. And so because of this, they cannot lose or gain electrons to do this. So therefore, they prefer to share instead. So this process of sharing is what we call covalent bond. So whenever electrons are not completely transferred, but instead they are being shared, then you have what we call a covalent bond. So remember in the last class when I was talking about ionic bond, if you look at potassium chloride, KCl, versus HCl, these guys seem like they are the same thing. In fact, by placement, hydrogen and potassium, they are in the same group in the periodic table. I've already told you about hydrogen, how special it is, that we place it in group 1, but really it does not necessarily behave that much like the group 1 guys. But let's accept that it's group 4 now. So KCl and HCl, it will be surprising that it is not the same type of bonding that exists between the two of these. KCl has ionic, while HCl is covalent. So what is the difference? What makes the difference? So in ionic bond, like I already told you, potassium is number 19. So it has 2 8, and then it has 2 8 8, then there is 1. So therefore it has 1 electron in its outermost shell. Then chlorine, it is number 17. So it has 2 8, and it has 7 electron in its outermost shell. So from what I taught you already, it can lose this 1 to this 7, and then this 7 will add 1 to it. So this one becomes Cl minus, and this one becomes K plus. But in the case of hydrogen, the electronic configuration of hydrogen is just 1. And so if it is to bond with chlorine, that means that it will have to donate its 1 electron to chlorine. I've already told you that they always favor the side with the smallest number of electrons based on the choice of whether to lose or to gain. So hydrogen, to complete its octet structure, it's either going to lose 1 or it's going to gain 7. But in the case of duplet structure, anyways, it's either going to gain 1 or lose 1. But the problem is that hydrogen cannot decide to lose 1 electron because that's all it's got. It only has 1 electron. So therefore, it is very, very not going to be wise for hydrogen to lose its only electron all in the name of I want to complete my octet structure. Because once you lose the 1, there is no inner shell for you to go and meet. So therefore, it is better that I remain incomplete than I lose everything that I have. So hydrogen does not have choice but to remain the way it is. So therefore, it is going to decide to share instead. So instead of just bonding with this chlorine and then transferring electrons to it, so it would prefer to share instead. And so before I talk about the sharing, let me teach you about the Lewis dot structure. So how does this work? The Lewis dot structure is basically writing electronic configuration in a fashionable manner. And then this time around, we only deal with the valence electron, the number of valence electron. So if you pick, let's say, I'm going to pick randomly like 3 different elements now. Let me start with chlorine. So we have chlorine, we have which one again? Which one again? We have oxygen. We have oxygen. Then we have so I'm going to pick hydrogen since I'm talking about hydrogen as well. I think I should pick nitrogen as well. So now, if you look at all these guys, chlorine belongs to group 7. So therefore, it has, when I say group 7, I'm talking about group 17. I've already explained all of these things in the previous video. You can always check it out. It's there in the playlist for the 50 days of tutelage. Some of the things I'm going to be talking about here, you might not grab them fully if you had not followed from the previous class. So chlorine has 7 electrons in its outermost shell. All you have to do is to just distribute them. So you just distribute them like this. So 1, 2, 3, 4, 5, 6, 7. So with chlorine now, you have all the 7 electrons complete in its outermost shell. And with that, you have done the Lewis-Dot structure of chlorine. For oxygen, it is in group 6, so it has 6 electrons in its outermost shell. So you have something like this. 1, 2, 3, 4. I think I should 1, 2, 3, 4, then 5, 6. So that's for oxygen. Then for hydrogen, it has only 1 in its outermost shell. So it has only 1. That one can be placed anywhere you like it. So you have hydrogen here. And finally, you have nitrogen. Nitrogen belongs to group 5. So therefore, it is 1, 2, 3, 4. Then let me just put 5 here. Now, this dot, 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 they signify electron. And these electrons, during the reaction, you can lose them, and then they can gain more electrons to complete their octet structure. I've already explained that in losing and gaining. So let's now consider hydrogen and chlorine now. I've already said that hydrogen will not be willing to lose its 1 electron. And also chlorine is a receiver. There's no condition which chlorine will donate its outermost electrons. So it's not possible. So therefore, the two of them come to an agreement. So it says, oh, I am chlorine. See, just get hydrogen's number and say, oh, hello, I'm chlorine. Can you see? It's already here. I'm chlorine. Can we bond together? And hydrogen will say, no problem. I would like to bond with you. And then hydrogen also comes here. And then the two of them come together. So what happens is that when they come like this, you now see that there is a shared electron between the two of them. There is a shared electron between the two of them. And this place is where you see the shared electron. This point is the shared electron. Now, this shared electron, you would think that, oh, one belongs to chlorine, one belongs to hydrogen. Yeah, that's true. But the moment they are sharing, we no longer say one belongs to, the two of them belongs to both of them. So on this right-hand side of chlorine, we have 2 electrons. On the left-hand side of hydrogen, we have 2 electrons. And so if you want to count the number of electrons that are around chlorine now, you are going to have, okay, I forgot this one here. 1, 2, 3, 4, 5, 6, 7, 8. Duplet structure, sorry, octet structure complete. And if you want to count the number of electrons that are around hydrogen, you have 1, 2. Duplet structure completed, because hydrogen it has only 1 shell. So it has only 1 shell, and that K shell can only contain 2 electrons maximally. Once it contains 2 electrons, then you say it is filled, just like helium. Helium is completely filled and it is stable. So therefore, stability is attained once 2 electrons are around the shell of hydrogen. And so with this now, you have what we call a covalent bond, because now both of them are sharing. Another thing about that is that each of them share the same amount of electron, meaning that if I'm bringing 2 electrons, you are bringing 2 electrons. If I'm bringing 3 electrons, you are bringing 3 electrons. That is exactly what it is like. Now, let's quickly do for H2O, water. But before I go to that, you see the bond that is formed, you always see a bond being drawn and all of those things. Is always done by 2 electrons. It's always done by 2 electrons. So these 2 electrons, they join together and they form a bond between hydrogen and chlorine. So you have HCl. This is a very, very perfect covalent bond. Now, let's do for water. So H2O. In this case, we're going to be having a central atom. The central atom is going to be the oxygen, because we have 2 hydrogen around it. So let's do a little bit of, we have oxygen here. The Lewis-Dot structure, 1, 2, 3, 4, 5, 6. So this guy wants to bond with 2 hydrogen. So we have hydrogen, this one has one here, hydrogen, this one has one here. For this guy to complete its octet structure, it needs two electrons. And good thing, two hydrogens are willing to come and pair with it. So therefore, they come together, they come close, and this guy comes here. So you have hydrogen here, this guy comes here, you have hydrogen here. So at the end of the day, what do you have? You're going to have 1, 2, 3, 4, 5, 6, 7, 8 around oxygen, so completed. 1, 2 around this hydrogen, 1, 2 around this hydrogen. So therefore, you have your H2O. So H2O, you also have what? You also have a covalent bond present in there. Now, what about for molecules, diatomic molecules? Yes, diatomic molecules. Examples like your chlorine, like your oxygen, even like your hydrogen himself. Once you see a diatomic element, any diatomic element, they would always have covalent bond. So their bond is always covalent. Diatomic covalent. I repeat again, diatomic covalent. So that is any atom that is bonding with itself will always be covalent, because if you begin to ask the question, who is going to receive, who is going to give out, it is the same element. So if one decides to give out, that means that the second two must give out. If one decides to receive, the second also must receive. So there's no settling the case between them. So therefore, they will always end up sharing. So just like if you have chlorine now, so you have chlorine 1, 2, 3, 4, 5, 6, 7. Another chlorine will come 1, 2, 3, 4, 5, 6, 7. So the two of them will come and they will share these two like this, and then they will become completed. And the same thing with oxygen. So you have oxygen 1, 2, 3, 4, 5, 6, and you have oxygen 1, 2, 3, 4, 5, 6. Now, what happened in this case is that this bond, even though I had written them separately here, when the bonding wants to take place, they kind of group and become a pair. These things are called lone pair. Anytime you have two electrons like this, they are called lone pairs of electrons. They are called lone pair of electrons. So that is, it is a pair of electron that is not being bonded, that is not being shared with anybody. Pair of electron is always two. Now, whenever they're not bonding with anybody, you call them lone pair. But for instance, now in this case, now these two electrons, they are a pair of electron, but they're not lone pair. They are shared pair of electron. They are shared pair of electron. I like to call them bonding pair. So what happened in this oxygen is that, so you can now rewrite it and make it like this. So you have 1, 2 here, lone pair, 1, 2 here, lone pair. Now, instead of the single electron here, you can decide to pair them together. Then the same thing, you have another oxygen like this, and then you have 1, 2, 3, 4, 5, 6. So you bond them together like this. So with this now, you are going to be able to now bond them together and say, okay, now you can now bond together oxygen, oxygen. So O2, then this will form double bond. So electron, electron, a double bond, a bond, another electron, electron, we have another bond. So therefore, you have a double bond. And by the way, you can count the number of electrons now. We have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So each of them now have 8 electrons each around them. So, and these guys are being shared. So this is a covalent bond. And we have what we call a sigma bond and a pi bond. I'm not going to be explaining that in this particular class. So that is the introduction to what covalent bond is. So I've already told you that there is always a sharing of electron. There's always a sharing of electron. So you can see that mostly hydrogen will share electrons. There are special cases whereby hydrogen form ionic bond, but in most of these cases, hydrogen is receiving electrons. Is receiving electrons. So where we have what we call metallic hydride, especially when it's bonding with group 2 elements, it forms what we call a metallic hydride. I'm not going to be going into details of that for this video, but note that two things that hydrogen will do majorly is to either share electron or receive electron. So it's not giving out any of those cases. It's not giving out. Now, so having explained that, there's one last one I want to explain. That is this guy, CO and CO2. So if you look at carbon, carbon is in group 4. So therefore, it's going to have 4 electrons around it. 1, 2, 3, 4. So you have oxygen. So I'm going to be using CO2 first. So you have oxygen. That you already know that this is 1, 2, 3, 4. Then we have 5, 6. Now, in the case of when this guy wants to bond together, so he wants to bond, one carbon wants to bond with two oxygen. So you are going to have, let's say, carbon. You're going to have this carbon. So this pair here. So the electrons are paired in this situation. And by the way, why am I writing them one, 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 one? I think in our electronic configuration, I've been able to explain one or two things. You know that carbon is element number. I think carbon is element number 6. Yeah, element number 6. And then, so if you write the electronic configuration, you have 1s2, 2s2, and you have 2p2. If you draw the orbital diagram, you have this is your 1s, this is your 2s, and in this place you have your 2p. From what I've explained to you, they will first of all be what? They will first of all be single before you start pairing them. And since it's only two electrons that are in the 2p subshell, then you only have this like this. Now, so therefore, this one guy, they are actually like valence electrons. There are 4 valence electrons, and then this one, they are there like that without pairing up with anything. Now, with this carbon now, if it wants to bond with oxygen, so what it does is that, just like I did in the case of O2 earlier, it groups its 4 electrons. It groups it like you have a lone pair on the left and a lone pair on the right. Now, when oxygen is coming as well, so the 2 oxygen can now come from left and from right. I think I should move my carbon down here so that I can have a better. So you have a lone pair on the right, a lone pair on the left. So you can bring oxygen here. So you bring oxygen here, 1, 2, 3, 4, 5, 6. You bring another oxygen here, you have 1, 2, 3, 4, 5, 6. So with this now, you have the CO2 form. So here you have a bond, you have a bond, here you have a bond, here you have a bond. So this case, you have what? You have what we call a covalent bond. A covalent bond. I'm sorry, how many covalent bonds do we now have now? So we have 1, 2, 3, 4. So 4 of them like that. And if you count, for carbon now, you have how many around it? You have 1, 2, 3, 4, 5, 6, 7, 8. Complete. For oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Like I told you, shared electron always belong to both parties. In the case of this guy, so we have C, we have this guy, double bond A, sorry, lone pair A, lone pair A. But it only wants to bond with one oxygen. So this guy have this guy have this, and this guy have this. So the question is that, are they going to bond in this way? So in this case, you have what we call the bond here, the bond here. If you look at oxygen, oxygen is kind of complete. So you have 1, 2, 3, 4, 5, 6, 7, 8. But for carbon, is it complete? You have 1, 2, 3, 4, and you have what? You have 5, 6. So in the case of this carbon now, what happened here is that there is a sort of donation. A donation of lone pair from one of the atoms that are sharing. Now, they've already shared equally. But one of the atoms will now donate its lone pair. It still has it. Don't forget, once it is a shared electron, it still belongs to that guy. So, but because this life is not balanced as far as carbon is concerned, so you notice that for this oxygen, there is 2 here, and there's 2 here, that's 4. There is 2 here, that's 6, there's 2 here, that makes 8. Oxygen has everything complete for it. But for carbon, we have 2 here, and we have 4 here. 2 plus 4 is 6. Octet structure is not yet done. So therefore, oxygen will now donate its lone pair for sharing. So this guy now becomes, so the lone pair is still here on the carbon. So you have C. So you have this were the electrons that they used to share equally before. So then oxygen now does not have the, what's it called again? It does not have the 2 lone pairs anymore. It donates the lone pair. So here you have the lone pair, 1, 2. These 2 guys belongs to oxygen, and only 1 lone pair is here. So lone pair has now become shared pair. In this case, what you have 3 covalent bond. 3 covalent bond. Now let's see whether it is complete now. In this middle here, you have 6. That means that carbon has 6, oxygen has 6. and both of them have two electrons on their outside. So that means that 6 plus 2 is 8. So therefore, both carbon and oxygen have now been able to complete their octet structure. And so your CO has triple covalent bond, but CO2 has double covalent bond, but on different sides. So this is how it works. This is now the only difference is now that in covalent bond, equal sharing. If I'm giving 2 electrons, the other one is giving 2 electrons. If I'm giving 4, the other one is giving 4, even though that one is opposite. I'm just saying. But in the case of this CO now, what you notice here is that even though carbon had given out 2 electrons to share, oxygen also gave 2 electrons initially to share. But oxygen had to go extra mile and donate a lone pair, that is 2 additional electrons for sharing. This last electron here is all from oxygen. They belong to oxygen. It is not a shared pair. So therefore, this bond is called dative or coordinate covalent bond. It's called dative bond or coordinate covalent bond. So coordinate covalent bond arises whenever a shared pair is done by one atom instead of being done by both of them. That is what you have dative or covalent bond. So I've been able to talk about this bonding pair and all of those things. Actually, there are some exceptions to octet rule, but I'm not going to be going into that details like BF3, PCl5. These are exception and all of those things, but I'm not going into all those things yet. Now, I want to talk about polarity of molecules. In okay. Before I think I should give one more example on this dative thing. Let's do NH3, ammonia. So you have NH3. So let's see what is going on here. Nitrogen belongs to group 5. So I think we've established that. So it has 1, 2, 3, 4, 5. And so 3 hydrogen can just come around it. So you have this hydrogen, you have another hydrogen, you have another hydrogen. So with this now, you have a perfect covalent bond. The only thing that is here is that there is a presence of lone pair around the nitrogen. So you still have 1, 2, 3, 4, 5, 6, 7, 8. This guy is not bonded, is a lone pair, but it has other guys bonded. And so this is a ammonia, purely covalent compound. But we now have NH4. This NH4 is always written as NH4 plus. That's why it's written as ammonium ion. In this situation, NH4 plus is actually going to be a what we call dative. So there's going to be an existence of dative bond in it. So in that situation, so if you bring another hydrogen now, hydrogen is supposed to have 1 electron being bonded with this one and sharing. So it's not going to happen. Hydrogen is just going to copulate with these 2 lone pair. And then it's 1 electron now, because this 1 electron that hydrogen seem to be what? To be having. So you can see we have hydrogen here, we have nitrogen here. So we now have this to be a radical, NH4 plus, NH4 plus. So meaning that it is needing 1 more electron. It is needing 1 more electron for it to have anything complete. So it is deficient of 1 more electron. So in this case, NH4 plus is what? Is a dative bond. I don't want to actually go into too much details of that. That's just like a side thing. Now, with this now, let's talk about shape of these molecules. Shape of molecules. We're going to be using the concept of what that we call the VSEPR theorem. VSEPR theorem. What is the VSEPR theorem? The VSEPR theorem is basically telling us about the valence shell electron pair repulsion. And this is going to help us know about the shape of different molecules. So to do this, what we need to identify is that we need to be able to identify, number 1, the number of electron regions that are present and the number of lone pairs that are present. But we always do this on the central atom. So know that any binary compound, so let's start with any binary compound, they are always linear. That's the shape of binary compounds. So we usually start from three and above. We usually start from three and above. So when I mean binary compound, I'm talking about has only two atoms, has only two distinct atoms in it. So that's what I mean by binary compound. For instance, if you have what's it called now? If you have HCl, if you have which one again is that? If you have nitrogen gas, oxygen gas, all these guys are what? They are binary compounds. They have two atoms. Two atoms. Now, H2O is not a binary compound. Yeah, it is only hydrogen and oxygen, but there are three of them. So two atoms of hydrogen and one atom of oxygen. So this guy does not follow. So, but for HClN2O2 CO, CO2 does not also follow. But all of these guys, they are binary, and therefore their shape is always going to be linear. So now let's proceed to the three guys. So what if you have three atoms? The first thing you need to always do is that. So let's start with H2O. So H2O, we know that oxygen is the central, and you have hydrogen here. You have this. I've already explained this guy. This. So you want to determine the shape of this. What you need to do is to look at the central atom. The central atom here is the oxygen, and look around it. How many electron regions do we have in this place altogether? How many electron regions do we have in this place altogether? We have 4 electron regions. We have 1, we have 2, we have 3, we have 4. So therefore, there are 4 electron regions around the central atom of H2O. And around this central atom, 2 of them are lone pairs. 2 of them are lone pairs. When you have this kind of combination, then the shape of that molecule is going to be bent. Sometimes it's also called angular. It's going to be bent, or also called what? Angular. Please take note of that. Bent or angular. Now, that's for 4 electron regions. So I want to give you a kind of list of what you actually need to know. Let me just put it here. Yeah, so there you go. Just go down right here. Yeah. So if you have 2 electron regions and 0 lone pair, it's linear. For example, if let's say we have this guy now, CO2. I've already explained that. CO2. So you can see that how many electron regions do we have here? We have 1 and we have 2. Are there any lone pairs around the carbon atom now? No. All of them are bonded or shared pair. So therefore, it's going to be a linear shaped guy. Which other one again? Ammonia. Let's look at ammonia. We have 1, 2, hydrogen, hydrogen, hydrogen. How many electron regions do we have altogether? We have 4. 1, 2, 3, 4. But among these 4, one of them is a lone pair. So therefore, you have 4 electron regions, and 1 lone pair. This is trigonal pyramidal. Trigonal pyramidal. So this guy is trigonal pyramidal. We also have tetrahedral. Like your CH4 now is going to be tetrahedral because you have 4 electron region and 0 lone pair on it. So you have tetrahedral. So you can always practice all of these guys when you are free. And that is that for shape of molecules on VSEPR. Now, let's talk about the last thing I want to talk about today. I think from the beginning of the class, I told you that I'm going to talk about covalent bond, Lewis dot structure, VSEPR theorem, and polar covalent bond. So that's the last thing I'm going to be talking about in today's class. So what is polar covalent bond? Polar covalent bond exists between 2 atoms that have very high difference in electronegativity. That is, the electronegativity of one is greater than the other. So what happens is that, for instance, if you have between hydrogen and oxygen now, these two, they share a bond together, but oxygen is quite electronegative more than hydrogen. So what happens is that when they are sharing these electrons, so you have electron here, you have oxygen. So oxygen tends to have a stronger pull on the electron to itself than hydrogen. So you have something of this nature. So you have hydrogen here, and the electron that they are sharing is here. let me use another color for that electron. So you have the electron that they are sharing, you have it here. So it is more closer to oxygen. So therefore, on this, you have what? You have this side of the entire molecule is behaving like a negatively charged part, and this side, because it's now electron deficient, is behaving like what? Um, a positively charged part. And therefore, in this place, in this molecule now, you have what we call a polar covalent bond. A polar covalent bond. So electronegativity, I've already explained that when I was teaching periodic table. For anytime you have two atoms such that one is of greater electronegativity than the other, then that guy will pull electron to itself. And because of this reason, it will become, that side will become like negatively a negative pole, and then the other side will be what? Like a positive pole. Then in that case, you have what we call a what? A polar covalent bond. A polar covalent bond. So I'm going to be limiting this class to this particular point. Don't forget to like, comment, subscribe, and share this video with your friends. I'll see you in the next class.